Hello everyone, welcome back to 𝗕𝗂𝘂𝘶𝗵, broadcast from SobolevSpaces. In this video I talk about inverse probability weighting in more detail. You will learn that weighting creates comparable samples of treated and untreated units. You will learn about its connection to stratification method. Make sure you watch until the end and compare the takeaways with your notes. As always, there is extra material. Click the link in the description and you will receive it. We define treatment effect as difference between average outcomes in all treated and all untreated units, and they are from the same study population. Here is a problem. The difference between sample means from treatment groups will not give us the treatment effect, simply because units in these groups are different. Instead, we resort to comparing potential outcomes of counterfactual treatments. We find the expected responses if all had been treated, and then if no one had undergone the treatment. We call them marginal means. This graph shows infant birth weight by mother's age and smoking history when pregnant. Green dots for non-smoking mothers and blue dots for the smokers. The dashed lines show simple means by smoking history, but we suspect that both smoking and weight depends on mother's age. Suppose age is the only common cause, then conditioning on it makes smoking history independent of its potential outcomes. Or put it differently, smoking can be thought of as randomly assigned within strata defined by age. For a moment, think of these 10 observations as the study population. There are 2 alternative treatments, and the outcome takes values on a continuous scale. Observations are grouped in 2 strata, S0, a lighter shade, and S1, the darker shade. The outcomes of alternative treatments are not available for the same study unit, so we cannot calculate individual effects and then average them. Nor can we use the difference in crude means between the treated and untreated, because strata and treatment effects could be mixed. Instead, we find marginal mean as an average of within strata means weighted by the strata prevalence. To make this specific, strata prevalence is 50% in our example, therefore the marginal mean, if all were treated, is the sum of conditional means multiplied by half, which is 14.3. Similarly, if all were untreated, the marginal mean equals the sum of conditional means times 1/2, which is again 14.3. As you can see, the crude means are different, but marginal means are not. You can think of it as assigning one of the 4 conditional means to units in each strata and treatment group. For instance, potential outcome of the treated would be 15.5 for units 1, 2, and 3, and 13 for units 9 and 10. Then marginal mean in treated is an average of these 10 outcomes. For the untreated, potential outcome would be 18 for units 4 and 5, and then 0.5 for units 6, 7, and 8. And the marginal mean is an average over all units. As the right table shows, we counterfactually assign the expected potential outcome for the study group to each unit in its stratum. This is stratification with averaging by strata prevalence. An alternative method is inverse probability weighting. Its central quantity is treatment probability within each stratum. We use its inverse value to weight observations. Outcomes with a lower treatment probability will have a higher weight. This is done to mimic the equal chance of being sampled as expected in randomization. This method also turns strata of treated and untreated units in comparable groups, but only if the strata are defined by treatment outcome confounders. Equal sampling chance for any covariate pattern in comparable treatment groups, you say? Well, then we can find marginal means as a weighted average of outcomes observed with and without treatment. To illustrate how this works, let's go back to the table with 10 hypothetical observations. The first step is to look at the treated, find the treatment probability and its inverse. In stratum S0, the probability of treatment is 2 out of 5. The weight for the stratum is 5/2. In stratum S1, the probability is 3 out of 5, and the weight is 5/3. The marginal mean is the weighted average of outcomes. The formula on the screen gives us 14.25. Next, the treatment probability for untreated. It's 3 out of 5 for S0 and 2 out of 5 for S1. Weights for the strata are 5/3 and 5/2. Again, the marginal mean is the average of weighted outcomes, which is 14.25 as well. Let's apply the inverse probability method to observations from the Birthweight by smoking study. The study variable is smoking history during pregnancy. The outcome variable is the birth weight, and we want to know whether smoking affects it. We have the same problem as in the previous chapter. We do not observe the counterfactual weights, that is, the weights of babies born to smokers had they not smoked, and the weights of babies born to non-smoking mothers had they smoked. They are presented by hollow squares here. If we calculate the mean for non-smokers using just the green dots, it will be biased downward, because we are ignoring the hollow green squares, and they correspond to larger weights. Therefore, we simply cannot use the sample means for smokers and non-smokers. If we did that, we would mix the negative effect of smoking with the positive effect of age, due to relationship between age and smoking. Instead, we use the inverse probability to correct sample means. We apply more weight to the solid green points for older ages and less weight for younger ages. By doing this, we pull up the sample mean for non-smoking mothers to find the marginal mean. We find it for smokers in a similar way, adding more weight for the younger ages. This graph shows dot sizes proportional to the inverse probability of smoking in age groups. Notice that the largest blue dots correspond to the youngest smoking mothers. They will have higher impact when we compute the mean weight of babies born to those with smoking history. Similarly, the green dots for older non-smoking mothers are larger. The dashed lines this time show the weighted averages for non-smokers and smokers. Let's compare side by side these two methods. The first is stratification with averaging by strata prevalence. We counterfactually assign sample means to all units in the stratum. Then we average within stratum means over the proportion of strata in the study population. In fact, we create two treatment groups with equal distributions of stratification variables. This can be best understood by the formula for aggregate counts. Suppose we have two treatment groups and two strata. Then we know the number of observations for each group in each stratum. Their sum is the number of observations in a strata. Their sum in turn is the number of all observations. Then we divide the number of outcomes by the number of observations in each treatment group within each strata. These are conditional outcome probabilities by treatment within strata. Then we divide the number of observations in the strata by the size of the study population. This is strata prevalence. We multiply these two and sum up their products over strata. Effectively, this means we compare the number of outcomes between treatment groups with the same presence of individual strata. The second approach is weighting observations by the inverse of their treatment probability. In practical terms, it means we correct the counts of observations and outcomes, so that all treatment groups will have the same prevalence of individual strata. Again, I use aggregate data to show this. We take the number of outcomes for the study group in a stratum. We divide them by the total number of observations. This is the joint probability for outcome, treatment, and stratum. We divide the number of observations in treatment group by the strata size. This is the probability of the observed treatment. Its inverse is the weight. We multiply the joint probability and the weight and sum up their products over strata. This means that the joint probability is corrected for equal chance of being sampled. But wait, that's not all. By rearranging the inverse probability formula, we can get exactly the stratification formula. Let's see. The first step is to remove the number of observations from the denominator. Then we swap the denominators of two ratios, and we get the product of two proportions. One is the outcomes in the study group within strata, and the other is the proportion of strata in the study population. Looks like stratification formula to me. So here is the main message of this video. The treatment probability weighting creates comparable samples of treated and untreated units. You learned that the weights are the inverse of the treatment probability. You also learned that applying the weights balances stratification variables in the treatment groups. Don't miss the central idea of the inverse treatment probability. Applying it to the study population creates equal chance for sampling every combination of stratification variables. Keep on watching.